Alright, so we're going to let our physics and equations keep track of this problem here. So we have a stone is dropped, we make stone 1, from a building, and so it's going to start to fall. Right? And so in the next frame, it's down here somewhere. The second stone is dropped. Now these are both falling. And we want to know how far apart these stones will be. What's the distance between them when the second stone, which is my greenish stone here, is traveling at a velocity of 12.9 meters per second. So what I'll do is I'm going to label these stone 2 and this one stone 1. So we're looking for V2 as determining our time. So V2 is going to equal the initial speed of the second stone plus acceleration. We're going to say the time for the second stone to fall. So we're tracking the individual variables here. We're going to solve this for time because that time is going to help us. And notice that there is a time difference here also of delta t. Delta t. Alright, so 1.55 seconds, there we go. So this will give us T2, which helps us determine some of the variables. So what we're looking at, all in all, is we need to find delta x, which is the difference between x1 and x2, the position of stone 1 and the position of stone 2. Our distance equation, again, notice I'm using my subscripts to keep track of each variable. So the distance equation that we're going to be looking at is x1 equals 1/2 a t1 squared. x2 equals 1/2 a t2 squared. And we'll subtract these, so delta x is equal to 1/2 a t1 squared minus 1/2 a t2 squared. Well, we have a GCF of 1/2 a here. Bring out 1/2 a t1 squared minus t2 squared. Well, I like this. This is a difference of squares. So I can represent this as 1/2 a times t1 minus t2 times t1 plus t2. And so our difference of squares lets us represent it this way. And so we have a nice compact way of talking about delta x. If we come back up here and we look at the velocity, we can have a compact way of talking about t2. Because v2 or vi is 0. And so v2 equals a t2. Well, we'll solve for t2. And we'll get v2 over a. Alright, so we're getting a lot of information out of our kinematic equations. And we've gotten them into two parts. We have the time for the stone to fall to the velocity that the problem's giving us. And we have the distance between them. But what we don't know is the time they fell. We just know the difference between the times T1 and T2. So we know a delta T of 1.55. If we drop the first stone, and then wait until we drop the second stone, 1.55 seconds, then T2 is always going to be T1 plus delta T. Because everything's in the case of T2 here, right? T2 is our stone 2 is the one that's giving us the most information. It's giving us the velocity. We'll rearrange this so that we have everything in terms of T2. So we'll say T1 equals T2 minus delta T. Well, now we can substitute this in here. And so we're going to substitute this for T2 and this for T1 into our delta x equation. So we get 1/2 A T2 minus delta T minus T2 times T2 minus delta T plus T2. So we've taken all this T1 and we've placed it into the T1s here and here. These T2s cancel. I get a negative delta T out front, so I'll pull the negative sign out here, negative 1/2 A. And I get 2 T2 minus delta T. Taking my definition of T2 up here, I can substitute that in. So I get negative 1/2 A delta T 2 V2 over A, there's my substitution, minus delta T. And so this velocity of stone 2 gives us the information we need to completely solve the problem. And so now when I plug in my variables, I get a negative 1/2 times negative 9.8 times 1.55, because that was the difference in time, 2 times 12.9 over negative, I'm double checking all my variables here as I poke them into the calculator, 9.8 minus 1.55. And I punch that in and I get 31.8 meters. The key to this is what we're doing is we're taking the information given, the delta T and the V2, and we're only requiring that to come in our equation here. And this can help simplify calculator errors or other things. It means we manipulate the equations a bit more, but we have the properties to be able to isolate our variables of interest.